The Black Hole War by Leonard Susskind, continued. Disc 3. Zero-point motion and the quantum jitters. A small vessel, perhaps a centimeter in size, is filled with atoms, helium atoms, which are very non-reactive, and then heated to a high temperature. Thanks to the heat, the particles whiz around, continually bouncing off one another and off the sides of the vessel. The constant bombardment creates pressure on the walls. By ordinary standards, the atoms move fairly fast. The average velocity is about 1,500 meters per second. Next, the gas is cooled. As heat is removed, energy is drained away, and the atoms slow down. Eventually, if we continue to remove heat, the gas will cool to the lowest possible temperature, absolute zero, or approximately minus 459.67 on the Fahrenheit scale. The atoms, having lost all their energy, come to rest, and the pressure on the sides of the vessel disappears. At least that is what's supposed to happen, but that reasoning fails to take into account the uncertainty principle. Consider this. What do we know about the position of an atom in the case at hand? Actually, quite a lot. Every atom is confined inside the vessel, and the vessel is only 1 centimeter in size. Obviously, the uncertainty in position, delta x, is less than 1 centimeter. Suppose for a moment that all the atoms really do come to rest as all the heat is drained away. Every atom would have zero velocity with no uncertainty. In other words, delta v would be zero. But that's not possible. If it were true, it would mean that the product m delta x delta v also would be zero, and zero is definitely less than Planck's constant. To put it another way, if the velocity of each atom was zero, its position would be infinitely uncertain. But it's not. The atoms are in the vessel. Thus, even at absolute zero, the atoms cannot completely cease their motion. They will continue to bounce off the sides of the vessel and exert pressure. This is one of the unexpected oddities of quantum mechanics. When a system has been drained of as much energy as possible, when the temperature is absolute zero, physicists say that it is in its ground state. The residual fluctuating motion in the ground state is usually called zero-point motion, but the physicist Brian Greene has coined a more descriptive colloquial name for it. He calls it the quantum jitters. Positions of particles are not the only thing that jitter. According to quantum mechanics, everything that can jitter does jitter. Another example is the electric and magnetic fields in empty space. Vibrating electric and magnetic fields are all around us, filling space in the form of light waves. Even in a dark room, the electromagnetic field vibrates in the form of infrared waves, microwaves, and radio waves. But what if we darken the room as much as science allows by removing all the photons? The electric and magnetic fields continue to do the quantum jitters. Empty space is a violently vibrating, oscillating, jittering environment that can never be quieted. Before anyone knew about quantum mechanics, they knew about the thermal jitters, which make everything fluctuate. For example, heating a gas causes the random motion of molecules to increase. Even when empty space is heated, it is filled with jittering electric and magnetic fields. This has nothing to do with quantum mechanics and was known in the 19th century. Quantum and thermal jitters resemble each other in some ways, but not in others. Thermal jitters are very noticeable. The thermal jitters of molecules and electric and magnetic fields tickle your nerve endings and make you feel warm. They can be very destructive. For example, the energy of the thermal jitters of electromagnetic fields can be transferred to atomic electrons. If the temperature is high enough, electrons can get ejected out of atoms. That same energy can burn or even vaporize you. By contrast, even though quantum jitters can be incredibly energetic, they cause no pain. They do not excite your nerve endings or destroy atoms. Why? It takes energy to ionize an atom, knock its electrons out, or fire your nerve endings. But there is no way to borrow energy from the ground state. The quantum jitters are what's left over when a system has the absolute minimum energy. Though incredibly violent, quantum fluctuations have none of the destructive effects of thermal fluctuations because their energy is unavailable. Black magic. To me, the queerest piece of magic in quantum mechanics is interference. Let's go back to the two-slit experiment that I described at the beginning of this chapter. It has three elements: a source of light, a flat obstruction with two small slits, and a phosphorescent screen that lights up when light falls on it. Let's begin this experiment by blocking off the left slit. The result is a featureless blob of light on the screen. If we turn the intensity way down, we discover that the blob is really a collection of random flashes caused by individual photons. The flashes are unpredictable, but when there are enough of them, a blob-like pattern emerges. If we open the left slit and block the right slit, the average pattern on the screen looks almost unchanged, except that it shifts very slightly to the left. The surprise occurs when we open both slits. Instead of just adding the left slit photons to the right slit photons and making a more intense but still featureless blob, our action results in a new zebra stripe pattern. One very odd thing about the new pattern is that there are dark stripes where no photons arrive, even though the same areas were filled with flashes when only one slit was opened. Take the point marked X in a central dark stripe. Photons easily pass through either slit and arrive at X when only one slit is open at a time. You would think that when both slits are open, an even larger number of photons would arrive at X. But opening both slits has the paradoxical effect of shutting off the flow of photons to X. Why does opening both slits make it less probable for a photon to get to destination X? Imagine a bunch of drunken prisoners staggering around in a dungeon with two doors to the outside. The jailer is careful never to leave one door open because some prisoners, as drunk as they are, will accidentally find their way out. But he has no qualms about leaving both doors open. Some mysterious magic prevents the drunks from escaping when both doors are open. Of course, this is not what happens to real prisoners, but it is the sort of thing quantum mechanics sometimes predicts, not just for photons, but for all particles. The effect seems bizarre when light is thought of as particles, but it is commonplace with waves. The two waves emanating from the two slits reinforce each other at some points and cancel each other at others. In the wave theory of light, the dark stripes are due to cancellation, otherwise known as destructive interference. The only problem is that light sometimes really does appear to be particles. The quantum in quantum mechanics. An electromagnetic wave is an example of an oscillation. The electric and magnetic fields at every point of space vibrate with a frequency that depends on the color of the radiation. There are lots of other oscillations in nature. Here are some common examples. A clock pendulum. The pendulum swings back and forth with one full swing taking about 1 second. The frequency of such a pendulum is 1 hertz, or 1 cycle per second. A weight hanging from the ceiling by a spring. If the spring is very stiff, the frequency can be several hertz. A vibrating tuning fork or a violin string. Either can achieve a few hundred hertz. The electric current in a circuit. This can oscillate at much higher frequencies. Systems that oscillate are called, not surprisingly, oscillators. Oscillators all have energy, at least if they are oscillating, and in classical physics the energy can be any amount. By that I mean that you can smoothly ramp up the energy, gradually if you like, to any desired value. But in quantum mechanics, it turns out that the energy comes in little, indivisible steps. When you try to gradually increase the energy of an oscillator, the result is a staircase instead of a smooth ramp. The energy can be increased only in multiples of a unit called an energy quantum. What is the size of the quantum unit? That depends on the frequency of the oscillation. The rule is exactly the same as the one that Planck and Einstein discovered for light quanta. The quantum of energy, E, is the frequency of the oscillator, F, multiplied by Planck's constant, h. E equals hf. For ordinary oscillators such as a pendulum, the frequency is not very great, and the step height, energy quantum, is extremely small. In that case, the staircase graph is made of such tiny steps that it looks like a smooth ramp. That's why you will never notice the quantization of energy in ordinary experience. But electromagnetic waves can have very large frequencies, in which case the steps can be quite high. In fact, as you may have already surmised, increasing the energy of an electromagnetic wave by one step is the same as adding a single photon to a light beam. To a classically wired brain, the fact that energy can be added only in indivisible quanta seems illogical, but that is what quantum mechanics implies. Quantum field theory. Laplace's 18th century vision of the world was a bleak one. Particles. Nothing but particles, moving in the unalterable orbits demanded by Newton's despotic equations. I wish I could report that today's physics provides a warmer, fuzzier image of reality, but I'm afraid that it doesn't. It's still just particles, but with a modern twist. The iron rule of determinism has been replaced by the arbitrary rule of quantum randomness. The new mathematical framework that replaced Newton's laws of motion is called quantum field theory, and according to its dictates, all of the natural world consists of elementary particles traveling from one point to another, colliding, splitting, and rejoining. It is a vast network of world lines connecting events, space-time points. The mathematics of this giant spiderweb of lines and points is not easily explained in lay language, but the central points are fairly clear. In classical physics, particles move from one point of space-time to another along definite trajectories. Quantum mechanics introduces uncertainty to their motion. Nevertheless, we can think of particles as traveling between space-time points, albeit along uncertain trajectories. These fuzzy trajectories are called propagators. We usually represent each propagator as a line between space-time events, but that's only because we have no way of drawing the uncertain motion of real quantum particles. Next come the interactions, which tell us how particles behave when they meet. The basic interaction process is called a vertex. A vertex is like a fork in a road. A particle proceeds along its world line until it comes to the fork, but then, instead of choosing one road or the other, the particle splits and turns into two particles, one for each branch. The best known example of a vertex is the emission of a photon by a charged particle. A single electron, spontaneously, without any warning, suddenly splits into an electron and a photon. Intuitively, we imagine that when something splits, each part is somehow less than the original. This is an idea inherited from common experience. The splitting of an electron into another electron and an additional photon shows how misleading our intuitions can be. That's the basic process that produces light. Jittery electrons splitting off photons. There are many other kinds of vertices involving other particles. There are also particles called gluons, which are found in the atomic nucleus. A gluon has the capacity to split into two gluons. Anything that can happen forward can also happen in reverse. That means that particles can come together and coalesce. For example, two gluons can come together and merge into a single gluon. Richard Feynman taught us how to combine propagators and vertices to form more complicated processes. For example, there is a Feynman diagram showing a photon hopping from one electron to another, which describes how electrons collide and scatter. Another diagram shows how gluons form a complicated, sticky, stringy material that holds quarks together in the nucleus. Newton's mechanics seeks to answer the age-old question of predicting the future given an initial starting point, including the positions and velocities of a set of particles. Quantum field theory asks the question differently. Given an initial set of particles moving in a certain way, what is the probability of different outcomes? But simply saying that nature is probabilistic instead of deterministic is not the full story. Laplace, although he would have disliked the idea, would have understood a world with a bit of randomness. He might have reasoned this way. The behavior of particles is not deterministic, but instead there is a positive probability for each distinct route leading from the past, 2 electrons, to the future, 2 electrons plus a photon. In ordinary probability theory, probabilities are always positive numbers. It's hard to imagine what a negative probability could mean. Try to make sense of the following sentence. If I flip a coin, the probability to get heads is minus 1/3. It's clearly nonsense. Then, following the usual rules of probability theory, Laplace would add up all the various probabilities to get the final, grand total probability. Such reasoning would make perfect sense to Laplace's classically wired mind, but it's not how things really work. The right prescription is bizarre. Don't try to grok it, just accept it. The correct rule is one of the consequences of the strange new quantum logic that was discovered by the great English physicist Paul Dirac immediately following the work of Heisenberg and Schrödinger. Feynman was following Dirac's lead when he gave a mathematical rule that computes a probability amplitude for each Feynman diagram. Moreover, you do add up the probability amplitudes for all the diagrams, but not to get the final probability. In fact, probability amplitudes needn't be positive numbers. They can be positive, negative, or even complex numbers. A complex number is one that contains the imaginary number I, which is the abstract mathematical symbol for the square root of -1. But the probability amplitude is not the probability. To get the overall probability, say for 2 electrons to become 2 electrons plus 1 photon, you first add up the probability amplitudes for all the Feynman diagrams. Then, according to Dirac's abstract quantum logic, you take the result and square it. The result is always positive, and it's the probability for the particular outcome. This is the peculiar rule that lies at the heart of quantum weirdness. Laplace would have thought it nonsense, and even Einstein didn't think it made sense. But quantum field theory is an incredibly accurate account of everything we know about elementary particles, including the way they combine to form nuclei, atoms, and molecules. As I said in the introduction, quantum physicists had to rewire themselves with new rules of logic. I don't really expect the lay reader to fully understand the rule or even why it is so strange. Nevertheless, I hope it will give some flavor of how the rules of quantum field theory work. Before closing this chapter, I want to come back to the thing that troubled Einstein so deeply. I don't know for sure, but I suspect that it had to do with the ultimate meaningless nature of probabilistic statements. I have always been mystified by what they actually say about the world. As far as I can tell, they don't say anything very definite. I once wrote the following very short story, originally included in John Brockman's book, What We Believe But Cannot Prove, that illustrates the point. The story, Conversation with a Slow Student, is about a discussion between a physics professor and a student who just can't get the point. When I wrote the story, I was thinking of myself as the student, not the professor. Student: Hi, Prof, I've got a problem. I decided to do a little probability experiment, coin flipping, and check some of the stuff you taught us, but it didn't work. Professor: Well, I'm glad to hear that you're interested. What did you do? Student: I flipped this coin 1,000 times. You remember you taught us that the probability to flip heads is 1/2. I figured that meant that if I flip 1,000 times, I ought to get 500 heads. But it didn't work. I got 513. What's wrong? Professor: Yeah, but you forgot about the margin of error. If you flip a certain number of times, then the margin of error is about the square root of the number of flips. For 1,000 flips, the margin of error is about 30, so you were within the margin of error. Student: Ah, now I get it. Every time I flip 1,000 times, I will always get something between 470 and 530 heads. Every single time. Wow, now that's a fact I can count on. Professor: No. What it means is that you will probably get between 470 and 530. Student: You mean I could get 200 heads? Or 850 heads? Or even all heads? Professor: Probably not. Student: Maybe the problem is that I didn't make enough flips. Should I go home and try it 1,000,000 times? Will it work better? Professor: Probably. Student: Oh, come on, Prof, tell me something I can trust. You keep telling me what probably means by giving me more probablys. Tell me what probability means without using the word probably. Professor: Well, how about this? It means I would be surprised if the answer were outside the margin of error. Student: My God! You mean all that stuff you taught us about statistical mechanics and quantum mechanics and mathematical probability, all it means is that you'd personally be surprised if it didn't work? Professor: Well, if I were to flip a coin 1,000,000 times, I'd be damn sure I wasn't going to get all heads. I'm not a betting man, but I'd be so sure that I'd bet my life or my soul. I'd even go the whole way and bet a year's salary. I'm absolutely certain the laws of large numbers, probability theory, will work and protect me. All science is based on it, but I can't prove it, and I don't really know why it works. That may be the reason why Einstein said God doesn't play dice. It probably is. From time to time, we hear physicists claim that Einstein didn't understand quantum mechanics and therefore wasted his time with naive classical theories. I very much doubt that this is true. His arguments against quantum mechanics were extremely subtle, culminating in one of the most profound and most cited papers in all of physics. My guess is that Einstein was disturbed by the same thing that bothered the slow student. How could the ultimate theory of reality be about nothing more concrete than our own degree of surprise at the outcome of an experiment? I have shown you some of the paradoxical, almost illogical things that quantum mechanics forced on a classically wired brain, but I suspect that you are not entirely satisfied. Indeed, I hope you are not. If you are confused, you should be. The only real remedy is a dose of calculus and submersion in a good quantum mechanics textbook for a few months. Only a very unusual mutant or a person brought up in an extremely peculiar family could naturally have the wiring to understand quantum mechanics. Remember, in the end, even Einstein couldn't grok it. Chapter 5. Planck invents a better yardstick. One day in the Stanford cafeteria, I noticed a number of students from my Physics for Pre-Meds class studying at a table. "What are you guys studying?" I asked. The answer surprised me. They were memorizing the table of constants, down to the last digit listed on the front cover of the textbook. The table included the following constants, plus about 20 more. H, Planck's constant, equals 6.626068 times 10 to the negative 34th power, meters squared kilograms per second. Avogadro's number equals 6.0221415 times 10 to the 23rd power. Electron charge equals 1.6021746 times 10 to the negative 19th power coulombs. C, speed of light, equals 299,792,458 meters per second. Diameter of proton equals 1.724 times 10 to the negative 15 meters. G, Newton's constant, equals 6.6742 times 10 to the negative 11th power, meters cubed, seconds to the negative 2nd power, kilograms to the negative 1st power. Pre-meds are trained to memorize huge amounts of material in their other science classes. They are good physics students, but they often try to learn physics the same way they learn physiology. The truth is that physics requires very little memory work.
I doubt whether very many physicists could tell you much more than the rough orders of magnitude of these constants. That raises an interesting question. Why are the constants of nature such awkward numbers? Why can't they be simple numbers such as 2 or 5 or even 1? Why are they always so small, Planck's constant, electron charge, or so large, Avogadro's number, speed of light? The answers have very little to do with physics, but a lot to do with biology. Let's take Avogadro's number. What it represents is the number of molecules in a certain quantity of gas. How much gas? The answer is an amount of gas that early 19th century chemists could easily work with. In other words, an amount of gas that could be contained in beakers or other containers that were more or less of human size. The actual numerical value of Avogadro's number has more connection with the number of molecules in a human being than with any deep principle of physics. Well then, why do humans have so many molecules? Again, it has to do with the nature of intelligent life, not fundamental physics. It takes a lot of molecules to make a machine complicated enough to think and ask chemistry questions. Another example is the diameter of the proton. Why is it so small? Once again, the key is human physiology. The numerical value in the table is given in meters, but what is a meter? A meter is the metric version of the English yard, which may have referred to the distance from a man's nose to his outstretched fingertips. Quite likely it was a useful unit to measure cloth or rope. The lesson from the smallness of the proton is merely that it takes a lot of protons to make a man's arm. From a fundamental physics point of view, there is nothing special about the number. So, why don't we change the units to make the numbers easier to remember? Actually, we often do just that. For example, in astronomy, the light year is used as a measure of length. I hate it when I hear light year misused as a unit of time, as in, gee, it's been light years since I saw you last. The speed of light is not so big when expressed in units of light years per second. In fact, it's very small, only about 3 times 10 to the negative 8th power. But what if we also changed our units of time from seconds to years? Since it takes light exactly 1 year to go 1 light year, the speed of light is 1 light year per year. The speed of light is one of the most fundamental quantities in physics, so it makes sense to use units in which c equals 1. But something like the proton radius is not very fundamental. Protons are complicated objects made of quarks and other particles, so why give them pride of place? It makes better sense to pick constants that control the deepest and most universal laws of physics. There is no dispute about what those laws are. The maximum velocity of any object in the universe is the speed of light, c. This speed limit is not just a law about light, but a law about everything in nature. All objects in the universe attract each other with a force equal to the product of their masses, and the Newton constant, g. All objects means all objects with no exceptions. For any object in the universe, the product of the mass and the uncertainties of position and velocity is never smaller than Planck's constant, h. The italics are there to emphasize the all-embracing character of these laws. They apply to any and all things, everything. These 3 laws of nature truly deserve to be called universal, far more so than the laws of nuclear physics or the properties of any specific particle, such as the proton. It may seem trivial, but one of the most profound insights into the structure of physics occurred in 1900, when Max Planck realized that specific units of length, mass, and time could be chosen in order to make the 3 basic constants, c, g, and h, all equal to 1. The basic ruler is Planck's unit of length. The Planck length is far smaller than the meter or even the diameter of a proton. In fact, it's about 100 billion times smaller than a proton. In meters, it's about 10 to the negative 35th power. Even if the proton were magnified to the size of the solar system, the Planck length would be no bigger than a virus. It is to Planck's everlasting credit that he realized that such impossibly tiny dimensions must play a basic role in any ultimate theory of the physical world. He didn't know what that role would be, but he might have guessed that the smallest building blocks of matter would be Planck-sized. The unit of time that Planck required to make c, g, and h equal to 1 was also unimaginably small, namely 10 to the negative 42nd power seconds, the time it takes light to travel 1 Planck length. Finally, there is Planck's unit of mass. Given that the Planck length and the Planck time are so incredibly small in ordinary biofriendly units, it would be natural to expect the Planck unit of mass to be much smaller than the mass of any ordinary object. But there you would be wrong. It turns out that the most basic unit of mass in physics is not terribly small on the biological scale, roughly the mass of 10 million bacteria. It's about the same as the mass of the smallest object that can be seen with the naked eye, a dust mote, for example. These units, the Planck length, time, and mass, have an extraordinary meaning. They are the size, half-life, and mass of the smallest possible black hole. We will return to this point in later chapters. E equals mc squared. Take a pot, fill it with ice cubes, seal it tight, and weigh it on a kitchen scale. Then put it on the stove and melt the ice, turning it into hot water. Weigh it again. If you do it carefully, making sure nothing enters or escapes the pot, the final weight will be the same as the original, at least to very high accuracy. But if you could do the measurements to 1 part in a trillion, you would notice a discrepancy. The hot water would weigh slightly more than the ice. To say it differently, heating adds a few trillionths of a kilogram to the weight. What's going on here? Well, heat is energy. But according to Einstein, energy is mass, so adding heat to the contents of the pot increases the mass. Einstein's famous equation, E equals mc squared, expresses the fact that mass and energy are the same thing measured in different units. In a sense, it is like converting miles to kilometers. The distance in kilometers is 1.61 times the distance in miles. In the case of mass and energy, the conversion factor is the square of the speed of light. The physicist's standard unit of energy is the joule. 100 joules is the energy required to illuminate a 100-watt light bulb for 1 second. 1 joule is the kinetic energy of a 1 kilogram weight moving with a speed of 1 meter per second. Your daily food provides about 10 million joules of energy. Meanwhile, the standard international unit of mass is the kilogram, slightly more than the mass of a quart of water. What E equals mc squared tells us is that mass and energy are interchangeable concepts. If a bit of mass can be made to disappear, it will be converted to energy, often in the form of heat, but not necessarily. Imagine that a kilogram of mass disappears and is replaced by heat. To see how much heat, multiply the single kilogram by the very large number c squared. The result is about 10 to the 17th power joules. You could live on that for 30 million years, or you could create a very large nuclear weapon. Fortunately, it is very difficult to convert mass into other forms of energy, but, as the Manhattan Project proved, it can be done. To a physicist, the concepts of mass and energy have become so closely identified that we rarely bother to distinguish them. For example, the mass of the electron is often quoted as a certain number of electron volts, the electron volt being a unit of energy useful to atomic physicists. With that knowledge, let's return to the Planck mass, the mass of a speck of dust, which we might as well also call the Planck energy. Imagine the speck being converted into thermal energy by some new discovery. The energy would be roughly the same as a full tank of gasoline. You could drive across the United States with 10 Planck masses. The unimaginable smallness of Planck-sized objects and the overwhelming difficulties of ever directly observing them are sources of deep frustration to theoretical physicists. Just the fact that we know enough to even ask these questions is a triumph of the human imagination, but it is this remote world to which we have to look for the key to the paradoxes of black holes, for it is Planck-sized bits of information that densely wallpaper the horizon of a black hole. Indeed, a black hole horizon is the most concentrated form of information that the laws of nature allow. Later we will learn what is meant by the term information and its twin concept, entropy. Then we will be in a good position to understand what the black hole war was all about. But I first want to explain why quantum mechanics undermines one of the most solid conclusions of general relativity, the eternal nature of black holes. Chapter 6. In a Broadway Bar. The first conversation I ever had with Richard Feynman was in the West End Cafe on Broadway in Upper Manhattan. The year was 1972. I was a 32-year-old, relatively unknown physicist. Feynman was 53. Even if no longer at the height of his powers, the aging lion was still an awesome figure. Feynman had come to Columbia University to give a lecture on his new parton theory. Parton was Feynman's term for the hypothetical constituents, parts, of subnuclear particles such as protons, neutrons, and mesons. Today we call them quarks and gluons. At that time, New York City was a major center of high-energy physics. The focal point was the physics department at Columbia. Physics at Columbia had a glorious and distinguished history. I. Rabi, a pioneer in American physics, had established Columbia as one of the world's most prestigious physics institutions. But by 1972, Columbia's reputation was in decline. The theoretical physics program at Yeshiva University's Belfer Graduate School of Science, where I was a professor, was at least as good. But Columbia was Columbia, and Belfer was far less exalted. Feynman's lecture was anticipated with enormous excitement. He held a very special place in the hearts and minds of physicists. Not only was he one of the greatest theoretical physicists of all time, but he was everyone's hero: actor, comedian, drummer, bad boy, iconoclast, intellectual giant. He made everything look easy. Everyone else would struggle through hours of complicated calculations to answer some physics problem, but Feynman would explain in 20 seconds why the answer was obvious. Feynman's ego was gargantuan, but he was great fun to be around. A few years later, he and I became good friends, but in 1972 he was a celebrity, and I was a star-struck stage door Johnny from the hinterlands north of 181st Street. I arrived at Columbia by subway 2 hours early for the lecture, hoping to have a few words with the great man. The theoretical physics department was on the 9th floor of Pupin Hall. I figured that Feynman would be hanging out there. The first person I saw was T.D. Lee, the Mandarin of Columbia Physics. I asked him if Professor Feynman was around. "What do you want?" was Lee's friendly response. "Well, I want to ask him a question about partons." "He's busy." End of conversation. That would have been the end of the story, except for nature's call. When I entered the men's room, I saw Dick standing in front of a urinal. Sidling up next to him, I said, "Professor Feynman, can I ask you a question?" "Yeah, but let me finish what I'm doing, then we can go into the office they gave me. What's the question about?" Right then and there, I decided that I really didn't have a question about partons. But I could concoct one about black holes. The term black hole had been coined by John Wheeler 4 years earlier. Wheeler had been Feynman's thesis advisor, but Feynman told me that he knew almost nothing about black holes. The very little that I knew I had learned from my friend David Finkelstein, one of the pioneers in black hole physics. In 1958, Dave had written an influential paper explaining that a black hole horizon was a point of no return. Among the few things I knew was that a black hole had a singularity at its center and a horizon surrounding the singularity. Dave had also explained to me why nothing could escape from behind the horizon. The final thing I knew, although I can't remember how I knew it, was that once a black hole formed, it couldn't split or disappear. 2 or more black holes could merge and form a bigger black hole, but nothing could ever cause a black hole to split into 2 or more black holes. In other words, once a black hole formed, there was no way to get rid of it. At about this time, the young Stephen Hawking was revolutionizing the classical theory of black holes. Among his most important discoveries was the fact that the area of the horizon of a black hole can never decrease. Stephen and his collaborators James Bardeen and Brandon Carter had used the general theory of relativity to derive a set of laws governing the behavior of black holes. The new laws had an uncanny resemblance to the laws of thermodynamics, laws of heat, although this similarity was presumed to be a coincidence. The rule about the area never decreasing was the analog of the second law of thermodynamics, which states that the entropy of a system can never decrease. I doubt that I knew of this work or even of the name Stephen Hawking at the time of Feynman's lecture, but Stephen's laws of black hole dynamics would eventually have a momentous effect on my research for more than 20 years. In any case, the question I wanted to pose to Feynman was whether quantum mechanics could cause a black hole to disintegrate by breaking up into smaller black holes. I was imagining something similar to the fragmenting of a very large nucleus into smaller nuclei. I hurriedly explained to Feynman why I thought it ought to happen. Feynman said that he had never thought about it. What's more, he had come to dislike the subject of quantum gravity. The effects of quantum mechanics on gravity, or gravity on quantum mechanics, were just too tiny ever to be measured. It wasn't that he thought the subject was intrinsically uninteresting, but without some measurable experimental effects to guide theory, it was hopeless to guess how it really worked. He said that he had thought about it years ago and didn't want to get started thinking about it again. He guessed that it might be 500 years before quantum gravity would be understood. Anyway, he said, he had to give a lecture in an hour and needed to relax. The lecture was pure Feynman. His presence filled the stage, a larger-than-life character with a Brooklyn accent and body language to illustrate every point. The audience was spellbound. He showed us how to think about difficult problems of quantum field theory in a simple, intuitive way. Almost everyone else was using another, older method to analyze the problems he was addressing. The older method was harder, but he had found a trick that made it all easy, the parton trick. Feynman waved his magic wand and all the answers popped out. Ironically, the older method was based on the Feynman diagrams. The best part of the lecture for me was when T.D. Lee interrupted to ask a question, or more likely to make a statement disguised as a question. Feynman had claimed that a certain kind of diagram never occurred in his new method, and that simplified things. It was called a Z-diagram. Lee asked, "Isn't it true that in some theories with vector and spinor fields, Z-diagrams don't always give zero, but I believe it can probably be fixed up?" The lecture hall was silent as a crypt. Feynman looked at the Mandarin for 5 seconds, then said, "Fix it." Then he went on. After the lecture, Feynman came over to me and asked, "Hey, what's your name?" He said that he had thought about my question and wanted to talk about it. Did I know a place where we could meet later? That's how we wound up at the West End Cafe. We'll come back to the cafe, but first I need to fill you in on some additional points about gravity and quantum mechanics. The question that I wanted to discuss had to do with the effects of quantum mechanics on black holes. The general theory of relativity is a classical theory of gravity. When a physicist uses the term classical, he doesn't mean that it comes from ancient Greece. It just means that the theory does not include the effects of quantum mechanics. Very little was understood about how quantum theory would influence the gravitational field, but what little was known had to do with small disturbances that propagate through space as gravitational waves. Feynman had contributed most of what we knew about the quantum theory of these disturbances. In Chapter 4, we learned that God apparently ignored Einstein about playing dice. The point, of course, is that things that are certain in classical physics become uncertain in quantum physics. Quantum mechanics never tells us what will happen. It tells us the probability that this or that will happen. When exactly a radioactive atom will decay is unpredictable, but quantum mechanics can tell us that it will probably decay in the next 10 seconds. The Nobel Prize-winning physicist Murray Gell-Mann borrowed this slogan from T.H. White's The Once and Future King. Everything not forbidden is compulsory. In particular, there are many events in classical physics that just cannot happen. In most cases, however, the same events are possible in quantum theory. Instead of being impossible, these events are just very improbable. But no matter how improbable, if you wait long enough, they will eventually happen. Thus, everything not forbidden is compulsory. A good example is a phenomenon called tunneling. Imagine a car parked on a hill with a dip in it. Let's ignore all irrelevant things such as friction and air resistance. Let's also assume that the driver left the handbrake off so that the car is free to roll. It's clear that if the car is parked at the bottom of the dip, it won't suddenly start to move. Motion in either direction would involve going uphill, and if the car is initially at rest, it won't have the energy to move uphill. If we later found the car rolling down the hill beyond the hump, we would assume that either someone had pushed it, or it had gotten the energy to go over the hump in some other way. Spontaneously jumping over the hump would be impossible in classical mechanics. But remember, everything not forbidden is compulsory. If the car was quantum mechanical, as all cars really are, nothing would prevent it from suddenly appearing on the other side of the hump. That might be very unlikely, and for a large, heavy object such as a car, it would be very, very unlikely, but it would not be impossible. Thus, given enough time, it would be compulsory. If we waited long enough, we would find the car rolling down the other side of the hump. This phenomenon is called tunneling, because it would be as if the car had passed under the hump through a tunnel. For an object as massive as an automobile, the probability that it will tunnel is so small that it would take an enormous amount of time, on average, for the car to appear spontaneously on the other side of the hump. To write a number big enough to express this amount of time would require so many digits that even if each digit were no bigger than a proton and they were solidly packed, the digits would more than fill the universe. However, exactly the same effect can allow an alpha particle, 2 protons and 2 neutrons, to tunnel out of a nucleus, or an electron to tunnel across a gap in a circuit. What I was imagining that day in 1972 is that although classical black holes have a fixed shape, quantum fluctuations can cause the shape of the horizon to jiggle. Normally, the shape of a non-spinning black hole is a perfect sphere, but a quantum fluctuation should be able to deform it briefly to a flattened or an elongated shape. Furthermore, every so often a fluctuation can be so large that the black hole will be deformed almost to a pair of smaller spheres connected by a thin neck. From there, it is easy for it to split. Heavy nuclei spontaneously split in this way, so why not a black hole? Classically, it cannot happen, just as the car cannot spontaneously hop over the hump. But is it absolutely forbidden? I could see no reason why it should be. Wait long enough, I reasoned, and the black hole will split into 2 smaller black holes. Now back to the West End Cafe. Nursing a beer, I waited for Feynman in the cafe for about half an hour. The more I thought about it, the more sense it seemed to make. The black hole could disintegrate by quantum tunneling, first into 2 pieces, then into 4, 8, and eventually a large number of microscopic components. In light of quantum mechanics, it made no sense to believe that black holes were permanent. Feynman entered the cafe just a minute or 2 early and came over to where I was sitting. I was in the mood to be a big shot, so I ordered 2 beers. Before I had a chance to pay, he pulled out his wallet and put down the required amount. I don't know whether he left a tip. I sipped my beer, but I noticed that Feynman's glass never left the table. I began by reviewing my argument and ended by saying that I thought the black hole ought to eventually disintegrate into tiny pieces. What could those tiny pieces be? Although it went unsaid, the only reasonable answer was elementary particles such as photons, electrons, and positrons. Feynman agreed that there was nothing to prevent this from happening, but he thought I had the wrong picture. I had visualized the black hole first splitting into more or less equal fragments. Each fragment would split in half until the fragments were microscopic. The problem was that a gigantic quantum fluctuation would be required for a large black hole to split in half. Feynman felt that there was a more plausible picture in which the horizon would split into a piece almost equal to the original horizon and a second microscopic piece that would fly away. As the process repeated, the large black hole would gradually shrink until there was nothing left. This sounded right. A tiny piece of the horizon breaking off seemed much more likely than the black hole splitting into 2 large fragments. The conversation lasted for about an hour. I don't recall saying goodbye, nor did we plan to pursue the idea. I had met the lion, and he hadn't disappointed me. Had we thought more about the problem, we might have realized that gravity would most likely pull the tiny fragments back down to the horizon. Some ejected fragments might collide with falling fragments. The region just above the horizon would be a complicated mess of colliding fragments that might be heated by the repeated collisions. We might even have realized that the region just above the horizon would be a seething mass of particles that formed a hot atmosphere. And we might have realized that this heated mass would behave like any heated object and radiate away its energy as heat radiation. But we didn't. Feynman went back to his partons, and I returned to the problem of what keeps quarks confined to the interior of protons. Now it is time to tell you exactly what information means. Information, entropy, and energy are three inseparable concepts that are the subject of the next chapter. Chapter 7. Energy and Entropy. Energy. Energy is a shapeshifter. Like mythical shapeshifters that could change from human to animal to plant to rock, energy also can change its form. Kinetic, potential, chemical, electrical, nuclear, and thermal heat are some of the many shapes that energy can take. It is constantly morphing from one form to another, but there is one constant. Energy is conserved. The sum total of all forms of energy never changes. Here are some examples of shapeshifting. Sisyphus is low on energy, so before pushing his boulder to the top of the hill for the umpteenth time, he stops to refresh himself with a meal of honey. When the boulder reaches the top, the condemned man watches while gravity rolls it back to the bottom for the umpteenth plus one time. Poor Sisyphus is doomed to eternally convert chemical energy, honey, to potential energy, and then to kinetic energy. But wait, what happens to the kinetic energy of the boulder when it rolls to rest at the bottom of the hill? It is converted to heat. A bit of heat flows into the atmosphere and into the ground. Even Sisyphus is heated by the effort. The Sisyphus cycle of energy conversion is as follows: chemical to potential to kinetic to thermal. Water flows over Niagara Falls and picks up speed. The flowing water, laden with kinetic energy, is directed into the mouth of a turbine where it spins the rotors. Electricity is produced and flows through wires into the grid. Can you chart the shape-shifting? Here it is. Potential to kinetic to electrical. In addition, some of the energy is uselessly converted to heat. The water that comes out of the turbine is warmer than the water that went in. Einstein proclaimed that mass is energy. What Einstein meant when he said E equals mc squared was that every object has some latent energy that can be released if somehow its mass can be changed. For example, a uranium nucleus will eventually break apart into a thorium nucleus and a helium nucleus. The thorium and helium will together have slightly less mass than the original uranium. That little bit of excess mass will morph into the kinetic energy of the thorium and helium nuclei, and also a few photons. When the atoms come to rest and the photons are absorbed, the excess energy becomes heat. Of all the usual forms of energy, heat is the most mysterious. What is it? Is it a substance like water, or is it something more ephemeral? Before the modern molecular theory of heat, early physicists and chemists thought that it was a substance and that it behaved like a fluid. They called it phlogiston and imagined that it flowed from hot objects to cool ones, cooling the hot and warming the cool. Indeed, we still speak of the flow of heat. But heat is not a new substance. It's a form of energy. Shrink yourself to the size of a molecule and look around at the hot water in a bathtub. You can see the molecules randomly moving and colliding in a bustling, chaotic dance. Let the water cool and look around again. The molecules move more slowly. Cool it to the freezing point, and the molecules become stuck in a crystal of solid ice. But even in the ice, the molecules continue to vibrate. They cease moving, ignoring quantum zero-point motion, only when all the energy has been drained away. At that point, when the water is at minus 459.67 degrees Fahrenheit, or absolute zero, the temperature cannot be lowered any further. Every molecule is rigidly locked in place, in a perfect crystalline lattice, all confusion and chaotic motion stopped. The conservation of energy as it shifts shape from heat to other forms is sometimes called the first law of thermodynamics. Entropy. It would be a bad idea to park your BMW in the rainforest for 500 years. When you came back, you'd find a pile of rust. That's entropy increasing. If you left the rust pile for another 500 years, you could be pretty sure it wouldn't turn back into a working BMW. That, in short, is the second law of thermodynamics. Entropy increases. Everyone talks about entropy. Poets, philosophers, computer geeks. But what exactly is it? To answer this question, consider the difference between the BMW and the heap of rust more closely. Both are collections of about 10 to the 28th power atoms, mostly iron, and in the case of rust, also oxygen. Imagine that you took those atoms and threw them together randomly. What is the likelihood that they would come together to form a working automobile? It would take a good deal of expertise to say just how unlikely that would be, but I think we can all agree that it would be extremely unlikely. Obviously, it would be far more probable that you'd get a pile of rust than a brand new automobile, or even an old rusty one. If you took the atoms apart and threw them together again and again and again, you'd eventually get a car, but in the meantime you'd get a lot more rust piles. Why is that? What's so special about the car, or the rust pile? If you imagined all the possible ways that you could assemble the atoms, the overwhelming majority of the arrangements would look like rust heaps. A much smaller fraction would resemble an automobile, but even then, if you looked under the hood, you would most likely find a rust heap. An even tinier fraction of the arrangements would form a working automobile. The entropy of a car and the entropy of a rust heap have something to do with the number of arrangements that we would recognize as rust heaps versus the number that we would recognize as a car. If you shook up the atoms of a car, you would be much more likely to get a pile of rust because there are so many more rust pile arrangements than car arrangements. Here is another example. An ape banging away at a typewriter will almost always type gibberish. Very rarely will he type a grammatically correct sentence such as, "I want to arbitrate my hypotenuse with the semicolon." Even less frequently will he write a meaningful sentence such as, "King Canute had warts on his chin." What's more, if you take the letters of a meaningful sentence and shake them up like tiles in a Scrabble game, the result will almost always be gibberish. The reason? There are a lot more nonsensical ways to arrange 20 or 30 letters than there are meaningful ones. The English alphabet has 26 letters, but there are simpler systems of writing. Morse code is a very simple system, using only 2 symbols, dot and dash. Strictly speaking, there are 3 symbols, dot, dash, and space, but one could always replace the space with some special series of dots and dashes that is otherwise unlikely to occur. Anyway, ignoring the space, you could write the description of King Canute and his warts in Morse code, with 65 symbols in all. How many distinct Morse code messages could be made out of 65 dots and/or dashes? All you have to do is multiply 2 together 65 times to get 2 to the 65th power, which is about 10 billion billion. When information is coded in terms of 2 symbols, they could be dots and dashes, ones and zeros, or any other pair. The symbols are called bits. Thus, in Morse code, King Canute had warts on his chin is a 65-bit message. If you are going to read the rest of this book, it would be a good idea to memorize the definition of the technical term bit. Its meaning is not the same as when you say, "I'll take a bit of cream in my coffee." A bit is a single, irreducible unit of information, like the dots and dashes in Morse code. Why do we go to the trouble of reducing information to dots and dashes, or zeros and ones? Why not use sequences of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or even better, the letters of the alphabet? Messages would be a lot easier to read, and they would take up a lot less space. The point is that the alphabet, or the 10 ordinary numerals, is a human construct that we learn to recognize and store in our memories. But each letter or numeral already has a great deal of information. For example, in the intricate difference between the letters A and B or the numbers 5 and 8. Telegraphers and computer scientists who rely only on the simplest mathematical rules prefer, in fact they are almost forced, to use the binary code of dots and dashes, or zeros and ones. Indeed, when Carl Sagan designed a system for sending messages to non-human civilizations living on distant solar systems, he used the binary code. Back to King Canute.
How many of the 65-bit messages are coherent sentences? I really don't know, perhaps a few billion, but whatever the number is, it is an infinitesimal fraction of 2 to the 65th power, so it's almost certain that if you take the 65 bits, or the 27 letters of King Canute had warts on his chin, and scramble them, gibberish will be the result. Leaving out the spaces, here is what I got when I did it with Scrabble tiles.
Hitkidjen kwan hitsurinesawachai.
Suppose you only scramble the letters a little at a time. The sentence will gradually lose its coherence. King Canute had warts on his chin is still recognizable. So is Knig Canute had warts o his chin. But gradually the letters will become a meaningless jumble. There are so many more meaningless combinations that the trend toward gibberish is inescapable. Now I can give you a definition of entropy. Entropy is a measure of the number of arrangements that conform to some specific recognizable criterion. If the criterion is that there are 65 bits, then the number of arrangements is 2 to the 65th power. But entropy is not the number of arrangements, in this case 2 to the 65th power. It is just 65. The number of times you have to multiply 2 together to get the number of arrangements. The mathematical term for the number of times 2 must be multiplied together to get a given number is called its logarithm. Thus, 65 is the logarithm of 2 to the 65th power. Entropy is, therefore, the logarithm of the number of arrangements. Of the 2 to the 65th power possibilities, only a very small fraction are actually meaningful sentences. Let's guess that there are a billion. To make a billion, you have to multiply together about 30 factors of 2. In other words, a billion is about 2 to the 30th power, or, equivalently, 30 is the logarithm of a billion. It follows that the entropy of meaningful sentences is only about 30, a good deal less than 65. Meaningless jumbles of symbols clearly have more entropy than combinations that spell out coherent sentences. It's hardly surprising that entropy increases when you scramble the letters. Suppose that the BMW company improved its quality control to the point where every car that came off the assembly line was identical to every other. In other words, suppose there was one, and only one, atomic arrangement that would be accepted as a true BMW. What would its entropy be? The answer is 0. There would be no uncertainty whatever about any detail when a BMW rolled off the assembly line. Whenever one specifies a unique arrangement, there is no entropy at all. The second law of thermodynamics, which says that entropy increases, is just a way of saying that as time goes on, we tend to lose track of the details. Imagine that we put a tiny droplet of black ink into a tub of warm water. At first, we know precisely where the ink is located. The number of possible configurations of the ink is not too large. But as we watch the ink diffuse through the water, we begin to know less and less about the locations of the individual ink molecules. The number of arrangements that correspond to what we see, namely a uniform, slightly gray tub of water, has become enormous. We can wait and wait, but we won't see the ink rearrange into a concentrated drop. Entropy increases. That's the second law of thermodynamics. Things tend toward boring uniformity. Here is yet another example, a bathtub full of hot water. How much do we know about the water in the tub? Assume that it has been sitting in the tub long enough that there is no detectable motion. We can measure the amount of water in the tub, 50 gallons, and we can measure the temperature, 90 degrees Fahrenheit. But the tub is full of water molecules, and there are obviously a very great number of molecular arrangements that correspond to the given conditions, that is, 50 gallons of water at 90 degrees Fahrenheit. We could know a lot more if only we could measure every atom precisely. Entropy is a measure of how much information is hidden in the details. Details that for one reason or another are too hard to observe. Thus, entropy is hidden information. In most cases, the information is hidden because it concerns things that are too small to see and too numerous to keep track of. In the case of the bathwater, these things are the microscopic details of the water molecules,
the location and motion of each of the billion individual water molecules in the tub. What happens to the entropy if the water is cooled until its temperature is absolute zero? If we remove every bit of energy from the water, the molecules will arrange themselves in a unique arrangement, the frozen lattice that forms a perfect crystal of ice. Even if the molecules are too small to see, if you are familiar with the properties of crystals, you can predict the position of every molecule. A perfect crystal, like a perfect BMW, has no entropy at all. How many bits can you stuff in a library? Ambiguity and subtle nuance in the use of language is often highly valued. Indeed, if words had perfectly precise meanings that could be programmed into a computer, language and literature would be impoverished. But precision in science requires a great degree of linguistic exactitude. The word information can mean many things. I think your information is wrong. For your information, Mars has 2 moons. I have a master's degree in information science. You can find the information in the Library of Congress. In each of these sentences, the word information is being used in a specific way. Only in the last sense of the word does it make sense to ask, where is the information located? Let's pursue this idea of location. If I told you that Grant is buried in Grant's tomb, we would no doubt agree that I have given you a piece of information. But where is that information? Is it in your head? In my head? Is it somehow too abstract to have a location? Is it diffused throughout the universe for anyone, anywhere to use? Here is one answer that is very concrete. The information is on the page, stored in the form of physical letters composed of carbon and other molecules. In this sense, information is a concrete thing, almost a substance. It is so concrete that the information in your book and in my book is different information. In your book, it says that Grant is buried in Grant's tomb. You may suspect that it says the same thing in my book, but you don't know for sure. Just maybe, my book says that Grant is buried in the Great Pyramid of Giza. In fact, neither book contains the information. The information that Grant is buried in Grant's tomb is in Grant's tomb. In the sense that physicists use the word, information is made of matter. When physicists use the word matter, they don't mean only things made of atoms. Other elementary particles such as photons, neutrinos, and gravitons also qualify as matter. And it is found somewhere. The information in this book is in a rectangular volume of space about 10 inches by 6 inches by 1 inch, that is, 10 times 6 times 1, or 60 cubic inches. These dimensions are a rough guess based on the size of the hardcover edition of my previous book. No doubt the actual dimensions of this audiobook are a bit different. How many bits of information are hidden between the covers of the book? In a line of print, there is room for about 70 characters, letters, punctuation marks, and spaces. At 37 lines per page and 350 pages, that's almost 1 million characters. My computer keyboard has about 100 symbols, including lowercase and uppercase letters, numbers, and punctuation marks. That means that the number of distinct messages that could be contained in this book is about 100 multiplied by itself 1 million times. In other words, 100 to the millionth power. That amount, a massive number, is roughly the same as multiplying 2 about 7 million times. The book contains about 7 million bits of information. In other words, if I had written the book in Morse code, it would have taken 7 million dots and dashes. Dividing that by the volume of the book, we find that there are about 120,000 bits per cubic inch. That's the information density in this volume of printed pages. I once read that the great library in Alexandria contained 1 trillion bits of information before it burned to the ground. Though not one of the official 7 wonders of the world, the library was nonetheless one of the greatest marvels of antiquity. Built during the reign of Ptolemy II, it is said to have contained a copy of every important document ever written, in the form of 500,000 parchment scrolls. No one knows who burned it down, but we can be sure that a lot of priceless information went up in smoke. Just how much? I'd guess that there were about 50 modern pages in an ancient scroll. If those pages were anything like the pages you were reading, a scroll was worth 1,000,000 bits, give or take a few 100,000. At that rate, Ptolemy's library would have contained 500 billion. 1 trillion equals 10 to the 12th power bits. Close enough to what I read. The loss of that information is one of the great misfortunes that scholars of the ancient world have to live with today. But it could have been worse. What if every nook and cranny, every available cubic foot, had been filled with books like this one? I don't know exactly how big the great library was, but let's say 200 by 100 by 40 feet, or 800,000 cubic feet, the size of a good-sized public building today. That would be 1.4 billion cubic inches. With that knowledge, it's easy to estimate how many bits could be stuffed into the building. At 120,000 bits per cubic inch, the grand total is 1.7 times 10 to the 14th power bits. Stupendous. But why stop with books? If each book were shrunk to 1/10 its volume, 10 times as many bits could be crammed in. Transferring the contents to microfiche could allow for even more storage, and digitizing each book might allow for even more. Is there a fundamental physical limitation to the amount of space needed to contain a single bit? Must the physical size of a real bit of data be bigger than an atom, a nucleus, a quark? Can we subdivide space indefinitely and fill it with endless amounts of information? Or is there a limit? Not a practical, technological limit, but a consequence of a deep law of nature? The littlest bit. Smaller than an atom, smaller than a quark, smaller even than a neutrino, the single bit may be the most fundamental building block. Without any structure, the bit is just there, or not there. John Wheeler believed that all material objects are composed of bits of information, and he expressed the idea with this slogan, "It from bit." John imagined that a bit, being the most basic of all objects, is as small as the smallest possible size, that fundamental quantum of distance discovered by Max Planck more than a century ago. A rough picture that most physicists have in their minds is that space can be divided into tiny Planck-sized cells, similar to a three-dimensional checkerboard. A bit of information can be stored in each cell. The bit can be pictured as a very simple particle. Each cell may contain a particle or not. Another way to think of the cells is that they make up a huge three-dimensional tic-tac-toe game. According to Wheeler's it-from-bit philosophy, the physical conditions of the world at any given time can be represented by such a message. If we knew how to read the code, we would know exactly what was going on in that piece of space. For example, is it what we normally call empty space, a vacuum, or is it a piece of iron, or the interior of a nucleus? Since things in the world change with time, planets move, particles decay, people are born and die, the message in the O's and X's also must change. At one instant, the pattern might look one way, a little later, it might be rearranged. In this Wheeler world of information, the laws of physics would consist of rules for how the configuration of bits is updated from instant to instant. Such rules, if correctly constructed, would allow waves of O's and X's to propagate across the lattice of cells and represent light waves. A large, solid lump of O's might disturb the distribution of X's and O's in its vicinity, and in this way, the gravitational field of a heavy mass might be represented. Now let's return to the question of how much information could be stuffed into the Alexandria Library. All we have to do is divide the volume of the library, 1.4 billion cubic inches, into Planck-sized cells. The answer is about 10 to the 109th power bits. That's a lot of bits, far more than the entire internet and all of the books, hard drives, and CDs in the world contain. Indeed, vastly more. To get some idea of how much information 10 to the 109th power bits is, let's imagine how many ordinary books it would take to store it. The answer is far more than we could possibly fit into the entire observable universe. The it-from-bit philosophy, describing a cellular world filled with Planck-sized bits of information, is an enticing one. It has influenced physicists on many levels. Richard Feynman was a great advocate of it. He spent a good deal of time building simplified worlds made of space-filling bits. But it's wrong. As we will see, Ptolemy would have been disappointed to learn that his great library could never have held more than a mere 10 to the 74th power bits. As it happens, that is about the number of bits that could be contained in a universe full of printed books. I can more or less picture what a million means. A cube, 1 meter on a side, contains 1 million gumdrops. But what about a billion? Or a trillion? It's harder to visualize the distinction, even though a trillion is 1,000 times bigger than a billion, and numbers like 10 to the 74th power and 10 to the 109th power are far too big to comprehend, except to say that 10 to the 109th power is a lot bigger than 10 to the 74th power. Indeed, 10 to the 74th power, the actual number of bits that could fit in the Alexandria library, is an infinitesimal fraction of the 10 to the 109th power bits that we computed. Why is there such an enormous discrepancy? That is a story for a later chapter, but I will give you a hint here. Fear and paranoia among kings and princes is an all too common theme of history. I have no idea whether Ptolemy suffered from it, but let's imagine how he might have responded to a rumor that secret information was being hidden in his library by his enemies. He might have felt himself justified in passing a draconian law that forbade any hidden information. In the case of the Alexandria library, Ptolemy's imaginary law would require every bit of information to be visible from outside the building. To satisfy the law, all of the information had to be written on the exterior walls of the library. The librarian was forbidden to hide a single bit in the interior. Hieroglyphs on the exterior walls allowed. Roman, Greek, or Arabic writing on the walls allowed. But scrolls brought into the interior? Forbidden. What a waste of space, but it was the law. Under these circumstances, what was the maximum number of bits that Ptolemy could expect to store in his library? To find the answer, Ptolemy had his servants carefully measure the external dimensions of the building and compute the area of the external walls and roof. Let's ignore the arches and the floor. They came up with 200 by 40 plus 200 by 40 plus 100 by 40 plus 100 by 40 plus 200 by 100, which equals 44,000 square feet. Notice that this time the unit is square feet rather than cubic feet. But the king wanted the area measured in Planck units rather than square feet. I'll do it for you. The number of bits that he could plaster on the walls and ceiling was about 10 to the 74th power. One of the most surprising and outlandish discoveries of modern physics is that in the real world there is no need for Ptolemy's law. Nature already provides such a law, and even kings can't break it. It's one of the deepest and most profound laws of nature we have discovered. The maximum amount of information that can be stuffed into a region of space is equal to the area of the region, not the volume. This strange restriction on filling space with information is the subject of Chapter 18. This book is continued on Disc 4.